So we'll pick up with our discussion of rapid spanning tree. Let's move on to the next slide. Now we'll talk about the port roles, and you'll recall in our lab I mentioned the port roles because it's listed in the newer iOS switches, even though the port roles really aren't used in 802.1d spanning tree. Now the root port and designated port in rapid spanning tree are exactly as they are in regular spanning tree protocol. The root port is the port that has the best path to the root, the lowest hop or the lowest port cost. The designated port is the same as spanning tree. It's the best port on a given network segment. And as you'll recall, rapid spanning tree uses the exact same criteria to determine the root and designated port. However, rapid spanning tree also introduces two other port roles. We have an alternate port and a backup port. Alternate port is the magic, if you will, of how rapid spanning tree converges so much more quickly. An alternate port is generally a discarding port. It's a switch port that's receiving a suboptimal path to root. Now this particular port type doesn't necessarily forward traffic for that segment. It does not necessarily have to be a designated port. It could be a discarding port. However, rapid spanning tree realizes I can still get to the root going through this alternate port. So if I lose my root port, after 3 times the hello timer or 6 seconds, I'm going to say, well, my path to root is gone. Do I have any alternate ports available to me that I can start forwarding traffic out immediately? Oh, look, there's an alternate port here that can still get to the root. I'll just switch and make him the root port, and it doesn't have to go through the whole discovery process like 802.1d spanning tree does. Now, obviously, if the switch doesn't have any alternate ports, it will still have to go discover a new root port, but most switches, if you have redundant links, will have an alternate port available to it. And the last new port type in spanning tree is the backup port, and I've got a little network diagram on the next slide that kind of makes this a little clearer, but a backup port is a switch port that's connected to a shared media segment, i.e. a hub. So if you have a switch and it has 2 ports connected into a hub, one of them is going to be a backup port. Obviously, it can't forward traffic out that backup port because it will create a loop in the network. So it's kind of like an alternate port, but it's an alternate port that's not connected to another switch. And as I promised, here's my lovely little network diagram. Looks suspiciously like the one in the regular spanning tree slide deck. Well, it pretty much is. Up here we have the root bridge, and you can tell because all of its ports are designated ports, so it is the root bridge. We have a hub over here as well, and we have our 2 non-root switches down here at the bottom. So obviously each of these switches have a root port pointing back to the root, like so. This switch over here on the left, however, is not the designated port switch for this network segment at the bottom. Even though it appears like it's just 2 switches connected together, you can imagine 125 workstations on this particular segment. However, because we are running rapid spanning tree, this switch over here has an alternate port. So this switch says, this port over here is not my root port. However, I can get to the root going through this switch port, just not as efficiently. So it will not forward any traffic on this port, but it will still listen to the BPDUs from this switch over here. If this link were to ever go away, this switch would know, well, I have an alternate. I'll just send the traffic out this direction. Now let's examine this link up here to this hub. Now, obviously, when this switch sends out BPDUs on this link, it goes over to the hub, just broadcasts everything that it receives out every port on the device. So it will send that BPDU out this other link back to the same switch. This switch will realize I sent a BPDU on this port, and I got the same BPDU back on this second port. Therefore, these 2 ports must connect to the same hub, so I'm going to flag this one as a backup. Now, it will not forward traffic out this port, as I mentioned. However, should this designated port go down, someone goes and unplugs this port from the hub on this end, this switch will realize I still have this backup port, and so I'll switch over and start using it immediately, much like this switch down here did with its alternate port. So let's examine rapid spanning tree in normal operation. Let's say we have a network with 4 switches, and they're all connected like so. You'll see this on a lot of networks. It's just daisy-chained like this. And let's say we as a network administrator see this setup and we go, well, that doesn't offer any kind of redundancy whatsoever. If this link here were to go down, this entire half of the network would just be disconnected. You'd split the network in half, and you couldn't get to the servers that were up here on this top switch. So we're going to implement some redundancy, and we put in another link between these 2 switches. Now, because we are running rapid spanning tree, this switch down here at the bottom right immediately says, hey, I'm starting to get BPDUs from the root bridge on this other port over here. I'll tell you what, I'm going to block all of my other ports to other switches, and if we had 5 or 6 other switches here, you can imagine the same thing on those links. I'm going to block all of my other uplink ports, and I'm going to tell this switch, you start sending all of your traffic for my MAC addresses out this port. And so almost immediately, you start using this new uplink port between the root bridge and the non-root bridge down here at the bottom right. Once this switch has determined that there's no loop on the network, it says, fine, I'll start sending BPDUs out all of my ports again. So it brings this link back up and starts sending BPDUs to this switch. Now this switch is receiving more optimal BPDUs for the root bridge coming from this direction as it would from this direction. So this switch here does exactly the same thing. It says I'm going to block all of my other uplink ports until I can determine that this path to root is more optimal than the one that I had before. And again, once this switch determines that there's no loops on the network, it then brings this port back up. But now it's getting BPDUs from both directions. So it says, well, you know what? This path here is just as efficient as this path here. So I'm not going to change anything unless one of these links down here happens to fail. Then I also have an alternate path back up to the root going this direction, and I can use it immediately without having that 20 seconds worth of convergence that regular spanning tree does. And that concludes our discussion of rapid spanning tree. Stay tuned. We'll put all this in a lab, and it'll get a lot more interesting, I promise.